Thank you so much for being here. We have Andrew Sellergren, who's a software engineer at Google Health, and has studied chemistry in college, joined Google as an analyst in 2010, and transferred into software engineering in 2014. He worked on large-scale infrastructure for Google Fit and Google Surveys before joining Google Health in 2019, and since then has worked on deep learning for chest X-rays, as well as externalizing training pipelines. So happy and excited to have you here and speaking on getting started with AI for medical imaging. So thank you so much, Andrew, and welcome.
Thank you. Yeah, I really appreciate your having me and organizing this. Yeah, we should have plenty of time today to get started with AI for medical imaging, and hopefully plenty of time for questions at the end. But also feel free to chime in with questions along the way, and I think Courtney or someone will, or Pooja will try to get my attention so that I can answer them in context. But yeah, as Sarah said, I have been at Google almost 13 years now, so seen quite a lot of changes, and also changed my kind of career track quite a bit. I was originally, so I guess I can go ahead and start this. I was originally going to go to medical school, and I decided that was not what I wanted to do, but I didn't know what I wanted to do instead. I was lucky to get a job at Google in 2010 as an analyst, and I learned a lot of programming on the job, and realized that was what I wanted to do more full time. Although, again, it was not any kind of lightning strike moment where I just knew that's what I wanted to do. And I still, in a lot of ways, see it as a tool among many others to get things done. So I was on Google Fit and Google Surveys in between, but in 2019 joined Google Health, and it's been a really wild and crazy ride since then. But particularly in the last couple of years, been working on deep learning for chest X-rays, which is what I'll kind of use as a way of getting you acclimated to this. So I'll also say I'm not really assuming any kind of background here. I mean, there will be some technical discussion points on either end, but hopefully I've given you enough to at least start down the path of some of these things. And I know there's probably a variety of backgrounds here, from medicine to basic science, or computer science, or informatics. So we'll just try to touch all our bases there. And so this also obviously wouldn't be possible without a huge team of people helping. It's pretty cool. One of the best parts about Google, well, actually the best part about Google, is definitely the people, but this is a very cross-disciplinary team. We have product managers who are also MDs. We have radiologists on staff. We have clinical scientists, research scientists, people who work in pure ML theory, and some in applied. So it's pretty cool to kind of have a meeting of the minds and work on stuff like this. That's definitely the best part. So I'll start basically at the highest possible level. I mean, and kind of explain why Google is in this space, or what we're aiming to achieve. And obviously, Google uses AI to improve experience in a lot of core Google products. So Photos is a great example of this, where you can search for personal photos without any tags or any additional metadata. Or with Google Translate, you can use live image to text translation. And then also hard problems in the physical world, like self-driving cars. And the medical space is one that kind of bridges both of those things. We on Google Health are really hoping to show what is possible, and then help others do the same. So it's an interesting place to be in at a large company like Google, obviously, because we're really not we're not in the business of kind of making products for the sake of generating revenue. A lot of this is meant to again show what's possible and inspire others and kind of be a force multiplier. And that's exactly what CXR Foundation is all about, which is the paper that I'll tell you a bit about more. So let's talk about AI for medical imaging and why did we start with chest X-rays? Why would it make sense to start with chest X-rays? So there's over 1 billion of these taken every year. They are fairly inexpensive, non-invasive, generally a fairly low dose of radiation, and they're readily available all over the world. But they vary in terms of image quality, the different populations and sites that are taking them, the devices that they're captured on, and there's a huge long tail of conditions that they're used for. So it makes for high quality interpretation being a pretty big challenge. There's a short supply of radiologists all over the world, and AI is definitely something that can step in and help bridge that gap. However, the problem is that building AI for medical imaging and chest X-ray in particular, it's very expensive. So often these models are tens, hundreds of millions, and now getting into the billions of parameters. Our work on a few of these different condition-specific models like tuberculosis shows that it often takes 6, 12, 24 months of time with a whole team of software engineers and research scientists to fine-tune them. And then you also need these very large, well-curated data sets. So the more the better, on the order of hundreds of thousands of images and thousands of expert labels. So all of this kind of makes it prohibitive to a lot of places to develop state-of-the-art medical imaging models or chest X-ray models. This is where Google can come in, and I'll explain how. But let's start, I guess, with sort of a fun exercise of, and I guess if there are any radiologists in the room, maybe they won't chime in, but we want to see how difficult this task actually is. And these are all images coming from Radiopedia, or most of them are, I think. Can anyone spot the abnormality here? They want to chime in?
There seems to be a wide triangle at the right of the middle. The bottom right seems wide triangle.
Oh, I see. You mean kind of like right here, or?
Yes, triangle. Yeah.
Yeah. I'm not actually sure. I mean, it could be a little bit of maybe like cardiomegaly, or maybe it's just a shadow. Anyone else see anything?
In the chat, we have David. David, do you want to unmute and say?
Oh, sorry. Yeah. Hey. I'm gonna guess the left lung mass, sort of in the mid lung.
Yeah. You're right. There's a nodule right there. Nodules are defined as small, less than 3 centimeters masses of tissues, and they can be benign or malignant. So it's not really possible to tell on a chest X-ray, and it could be something that's just sort of incidental. But yeah, you can see it's pretty difficult to see there amongst all this other stuff going on. Okay, how about here? Anyone know what's going on here?
Pneumothorax. Pneumothorax on the left.
Nice. Yeah, that one's a little bit easier to see. Basically, the collapsed lung, air leaks into the space between your lung and the chest wall. So you can see this obviously looks far different from this other side. And this is a very serious condition that needs attention right away. This one I'm not even going to ask because it's so hard, especially at this resolution. It's kind of not fair. But There's a fracture way down here on one of the ribs. And then anyone know what's going on here or have any guesses?
We have prominent and interstitial lung markings.
I don't even know actually what that means. So I will defer to your knowledge. But yeah, there are peripheral and lower lobe airspace opacities. I don't know if that's kind of what you were referring to, or also I don't know.
Yeah, ARDS, and kind of goes with your COVID diagnosis. This looks like someone who's got ARDS or is developing the early stages of ARDS, acute respiratory distress syndrome.
Okay, awesome. Well, I'm sorry, that's not awesome, but you know what I mean. Yeah, so I'm hopefully proving my point, because I don't even know the 1% of all these kinds of things, and it's a very hard task and something that we are still teaching ourselves as well as machines to do. But this is a COVID-19 diagnosis here. So I have all these links, and I'll share this deck out afterwards as well. So now that we know how hard this task is, what can we do to help, and Google can do to help? So our mission is to enable others to train custom chest X-ray models, and we want them to be able to do it with less data setup and compute. And so, as I mentioned before, with our very large models, our hundreds of accelerators that they sometimes require, it feels a little disconnected to sometimes for us to put out papers that have these, this really large scale training that technically can be reproduced, but most people, it's inaccessible to most people. And it also may be that the places that need this the most have the biggest gap to accessibility there, right? So we want to not only train models that are really powerful, but actually get them to places that they can be used. So how do we go about doing that? We kind of talk about 3 axes here. One is to decrease the training time. We want to improve label efficiency. So labeling is a very high cost. I mean, as you just saw, we need experts who can read these images, and getting a few thousand labels is often really difficult, let alone millions. And then finally, we want to also reduce the model complexity. So places where you may not be able to train a 1 billion parameter model, how can you do something instead? So our method is pretty simple in terms of a kind of a common sense approach. Is basically we want to offload as much of this heavy lifting as possible to a place like Google that can do this. So we do our CXR specific pre-training, and we generate embeddings instead of going all the way to a classification prediction, basically. So what are embeddings? Embeddings are vectors of features that can be represented just as floating point numbers. This, just a long array of numbers, basically. In our case, it's actually 1376 is an artifact of this network that we're using. I'm going to try to say this as many different ways as possible to hopefully hit all the different fields. But basically, mathematically, it's a projection into this 1376 dimensional space. Conceptually, it's basically like taking the original chest X-ray, which might have been 3000 by 4000 pixels, and we will do some pre-processing like cropping and resizing down to like 1024 by 1024. So, roughly 1 million pixels there. And then we're compressing it down into 1376 numbers. So it's a, very high quality compression, basically, of the original image. And the numbers in that embedding represent features. So it's a little difficult to talk about what that means, because these features aren't really human understandable, at least at the moment. You know, the dream would be that they would be. And they're also kind of entangled. You know, it's not like one number in this array of 1300 represents one particular feature. But you can think about features as things like we just saw on the chest x-rays, like maybe there's some combination of features that, or a combination of those numbers that represents, is there a nodule? Are there peripheral airspace opacities, fracture, those kinds of things. Some of these are, you know, findings or conditions, and some of them are maybe even almost full diagnoses or classifications. But my argument to you today will be that this kind of setup, where you have a very large foundation model followed by some frozen, you know, downstream training, potentially using these things like embeddings, is a really transformative approach, really powerful, and maybe the way things are going these days. And you know, the last couple of times I've given this was before ChatGPT, but you know, I would kind of be remiss to not at least mention it and talk about what I think that means. So I do think that actually the power behind a lot of these large language models, whether it's from Google, Microsoft, wherever, I think it can come down to these really, really powerful encoders or you know, compression tools. Basically, you know, these models can represent a way of extracting very general features from your data without necessarily knowing what the downstream task is. So if you take away nothing else from this, I would take away that my opinion, you know, again, also not a representative of Google in this, but my opinion is that the embeddings here are the powerful thing. And I would definitely encourage you, you know, all of the large language model hype is very cool, but we should start thinking about kind of what's next. You know, I don't know that chatbots are the natural end of this. I think what they reveal is how strong these models are and the kinds of features that they encode. But what's next? You know, what can we do with that, particularly in a space like medicine that really, really could benefit from it. So I'll kind of breeze through this. I don't think this is too interesting, but you know, in a typical setup, you might envision a model here being a collection of neural network layers. We've just sort of visualized it as a pyramid here. And at the base, we're putting in our chest x-ray image. And at the apex of the pyramid, you traditionally would have a prediction like airspace opacity or fracture or what have you. What we've done is essentially just say, okay, let's just chop off the top few layers, and the last layer then is your embedding. So this is where you get your feature map, your array of numbers that represents kind of hopefully a lot of really salient things about that original image. So this is a really cool animation that someone at Google generated for us, where the idea being that if you on a typical approach on the left, you would need to kind of restack all of these layers over and over again in order to accomplish different tasks. So you know, even as of a couple years ago, we found that if you wanted to train models for pneumothorax, airspace opacity, tuberculosis, you often had to not necessarily start from scratch, but start from ImageNet, or you know, basically retrain exclusively on that task. And the models themselves didn't do very well on multiple tasks. But with approaches like CXR Foundation, where you try to aim for a more generic pre-training that still is in your domain of interest, in this case, chest x-ray or medical imaging, you can end up with sort of a solid base of this pyramid. And then your tasks, you just insert on top. And I can show you how, well, I'll show you in a minute how powerful that can be. But just to dive into the technical piece real quickly, the type of learning that we used on this was called supervised contrastive learning. So in general, we aimed ourselves toward the contrastive learning because our goal was kind of to optimize this embedding space rather than the downstream tasks. So there's a lot of benefits to contrastive learning for any particular task of interest. But in terms of more directly optimizing the embedding space, we found that the contrastive learning was a really good option for this. So in this case, again, don't let the complex diagrams fool you. It's a pretty simple concept. The idea is that you have an image that gets compressed down to this embedding space. And once it's in that space, we're going to bring images that we want to be similar to each other together in that embedding space, and then push the ones that are different away from it. So in the natural image case, this could be dogs and cats. We want to bring all the dogs together in this embedding space and push the cats away. In our case, it was abnormal images and normal chest X-ray images. So the reasoning being there that most chest X-ray classification tasks boil down to a sort of subclass of abnormal. If you can determine that an image, a CXR is normal, you may be able to kind of move on and avail yourself of other techniques and modalities, but the chest X-ray part might be kind of done. Whereas with the abnormal, then you start diving into, okay, what are the specific findings and classifications we can do from that. So let's make an effort to actually just visualize these embeddings. So as I mentioned before, this is kind of a 1300-ish dimensional space that we basically put these chest X-rays into. And there's a variety of techniques for visualizing these really high dimensional spaces. One of which is T-distributed stochastic neighbor embedding, T-SNE. And this is just basically a way of kind of reducing all of those dimensions down to two dimensions, so that we as humans can kind of look at it a little bit better. So practically speaking, again, what does this mean? Well, on the left, if we start with a model that was trained on natural images like ImageNet or JFT, and then we try to visualize, okay, where does that put the airspace opacity classes in this embedding space? The red and the blue represent positive and negative. So the salient thing here is that on the left, it's pretty hard to find your way around separating these out, right? I mean, ideally you can train a nonlinear classifier that can do something like that, but it's not very well organized there. Whereas over on the right with your chest X-ray network embeddings, even before we've made any kind of additional, provided any additional labels to the network, it's kind of already separated airspace opacity, positive and negative. And you can really almost just draw a squiggly line between these two classes. And that's kind of exactly what you want to be able to do. Again, let's talk about kind of how powerful this is and what we can do with these things. So we tested this on 6 different types of findings on chest X-rays, as well as 2 downstream diagnoses that the model hadn't explicitly seen yet, which were tuberculosis and COVID-19 severity. So as you can see in the top figure, really up until about the 10,000 image mark, you don't get much benefit from training exclusively on that downstream task of interest. So, let's say you, again, wanted to train a airspace opacity classifier. You really need at least, roughly 10,000 images. There's a lot of confounding things here, the types of networks that we used, how much time we put into training them. But I also think that that's actually again, a reason to consider an approach like this, because there may be a more optimal network that trains exclusively on those 10,000 images, but it's going to cost you a lot of time and effort to find. Whereas you may get a pretty good result, a decently performant model starting with a frozen encoder like we have with CXR Foundation. And similarly with tuberculosis and COVID-19, we were able to show that even with a couple dozen, maybe a couple hundred, you get pretty good results with more difficult tasks like tuberculosis and COVID-19. Here I'll show a little bit more about this later, but on this graph we have the radiologist operating points. So we were able to show that, okay, you can actually take just 45 images from a completely different training set of Shenzhen and Montgomery are two openly available public tuberculosis data sets, and you can train on one and test on the other. They come from different countries as well. So it shows pretty good generalization, and you can see, does about as well as the radiologists, even with only a few images to learn from. And similarly, some of the backstory here was that we started this exploration back in 2020 because we were developing our abnormal normal model, trying to again, generalized to kind of all the different long tail of conditions. And then when the pandemic broke out, we wondered if there was anything we could do to help. We quickly, talked to our collaborators, got a few hundred images from their hospitals that were COVID-19 positive. And, this was a great exercise in showing kind of what I still think of as the great part of working at Google, is that we were able to talk to clinicians, radiologists, and the end result was basically, yes, we can predict COVID from chest X-ray, but it's not necessarily particularly clinically useful. You don't go, even when there was a dearth of testing in the very beginning, you wouldn't show up to a hospital and just immediately get a chest X-ray. It's not part of the normal clinical workflow. So, as exciting as some of these models are, we really want them to be informed by what is clinically useful, what is going to have an impact. So we at least pivoted a little bit and kind of showed that, okay, assuming that they were already maybe admitted to the ICU, can we predict severity from chest X-ray? And we found pretty good results there. And generally, this use case was a good proof of concept for our approach, because the COVID-19 pandemic has, we've never seen such a, consistent and ongoing distribution shift, really, right? I mean, after early 2020, when there became new variants that started to emerge, there were different demographics that were affected by the disease. There were obviously vaccination status then became a factor. So, this disease showed how this distribution can change so quickly that you want to be able to have a model that can quickly adapt with maybe only a few dozen or a few images. So we hope that that's kind of a good proof of concept there. So I will just very quickly talk about the kind of next step of this, and then show a hopefully exciting demo, because I think even since we published the paper, within a month or two, there were new techniques that were even more powerful and exciting. We tried this clip loss, which is also shown in this convert paper and check zero, which I'll link to. And the idea is to take this contrastive loss and be kind of one step further. So here we have our same image encoder, which is our large convolutional neural network in our case. And before, we were bringing together images that were abnormal and pushing ones that were normal away. Now we've kind of made it a little bit more nuanced and said, okay, let's use the radiology report as the thing to kind of bring things together. So instead of the just 2 images that we brought together, we actually bring together an image with text in the same embedding space. So the image goes through this encoder, we put it into the embedding space. The text, which is the radiology report, goes through a model, gets put into the embedding space. And then we try to make those as similar as possible when they are a pair, right? And this turns out to be incredibly powerful. I mean, it's been shown to be very useful in the natural image domain and produce these really, really strong models. But here we also are able to then build some really, really cool things on top of it, including zero-shot image classifiers, text-to-image retrieval tools, even report generators. So in lieu of the this GIF, I'll actually just go ahead and show this. Okay, so what do we mean when we say zero-shot? It's a bit of a, in my opinion, it's a bit of a misnomer here because so zero-shot typically means that you're asking a model to give a prediction or do something on data that it's never really seen before. So the cases that I just described of we took a few dozen or a few hundred images and trained a downstream model. Those would be classified as few shot, where few is like a few hundred, meaning you just give the model a few examples to learn from. The zero shot case is meant to be, well, we gave you no more you get no more examples of this, but we just ask you directly to give a classification. So in this case, it's a bit of a misnomer because the model, at least for some of these cases, some of the conditions, has seen that condition. So it's never seen COVID, but it has seen things that look like COVID on chest X-rays. It has seen tuberculosis, although we didn't explicitly call it tuberculosis. But then we're going to ask it to do diagnoses on those things without any further training. So the cool thing about this is that if you're familiar at all with the new stuff going on with large language models, it resembles a lot of this kind of prompt engineering, which in my personal opinion, I hope is kind of an artifact that goes away and we don't have to worry about it too much anymore, because I don't really want to be a prompt engineer. But the idea is that for any particular classification case, we're not using the radiology reports from this data set at all. So this is the Chexpert data set. It's a publicly available data set. It hasn't trained on Chexpert at all. It won't have seen the radiology reports for this at all. We will use the labels, but only for the evaluation. So only to know kind of whether this is correct or not. So we design a prompt that we expect will kind of cover the positive case. So in this case, for pleural effusion, we just say, oh, there's a left pleural effusion or a right pleural effusion. And then we say for the negative case, something that's hopefully fairly straightforward, like no pleural effusion. Although it's a little tricky because you may not explicitly call out the negative case in a radiology report. But let's go ahead and run this. Now, so what this is doing on the back end is taking those prompts, passes them through the language model, gets embeddings, and then it tests to see kind of which one is closer to the image embedding. So if it's closer to the positive case, you might get a higher positive score. If it's closer to the negative case, you might get a higher negative score. So that's sort of how we're determining our classification score here. And what's cool is that you get really strong results even with this kind of prompt engineering approach. And we can even do this on the fly. So I can, for example, I want to also make sure that if any report just says that it's normal, let's go ahead and include that in the negative. So you saw there, my score was 0.9-ish. That's the area under the curve. and it represents a trade-off between the false positive rate and then the true positive rate. So some of the scores that I was reporting earlier were all AUCs, and again, they're kind of on the same level here, even though here we're doing it 0 shot, and there we were doing it with a few dozen or a few hundred images. So let's see what happens when we add the normal. Okay, so you can see we immediately added, almost 2 AUC points, which is pretty cool. So the use case that I see, or one of the use cases that I see here being pretty cool, is that, in a sense, you are training your model using this kind of natural language. And I think this is a lot more accessible to folks like clinicians or, the ones that have the real expertise that in that domain, versus the ones who trained the model, like me, who don't have the clinical expertise, but have the ML side of things. So you could imagine, well, maybe I take my data set, I have a few dozen or 100 images that I just label for whatever condition. And I validate that my prompts represent a decent classification of this. Then I can apply that to a much larger data set of thousands, hundreds of thousands, and then you can fine tune and get your more performant classifier. So this is the kind of thing, these sort of auto ML-ish or kind of no code ML training is very compelling, because again, we want to get this into the hands of the folks who, and again, this is also not being trained on a massive accelerator cluster. This is just running on a laptop. So the other cool thing that we can do here is, so this, again, is not using any of the radiology reports, but we can search as if they had radiology reports. So we can search in natural language and ask it to give us images that resemble that. So if I say, give me normal images, again, it's going to pass that through the the text encoder, get your embeddings back and kind of see which is the most similar to that word normal. But it's directly querying the image embedding space. So you can see you get relatively normal looking images here. And you could do something like to show you images that have an endotracheal tube. And here, one cool use case might be that if you were in a EHR system or what have you, you could call up similar images or ask it to kind of show you an example of something that was more salient to whatever you were looking at, that might be different from the image you're actually seeing at the moment. But also, this is the part where we're kind of trying to get the word about this stuff out there, because we don't know what the most exciting, amazing application of this could be. And we want to hear from the folks who, there's a good chance that people will say, no, I don't want anything to do with that. Or, that won't work for me. Here's what I want. And that's what we want to hear. I don't want to just be kind of building models for the sake of building models. But hopefully that shows you kind of the power of these models that we have here. Only a few years ago, this kind of score would only have been possible with training off of millions of images. And now we can do it in a very, 0-shot way. I kind of ran through all of that, but we'll have plenty of time for questions. So I want to definitely thank the folks outside of Google who have also contributed to this effort in their ways, which by offering these open access data sets like Mimic CXR and Checkspert. So they enable us to show a lot of these really cool results and demos. And we also work directly with the Mimic CXR folks to release the embeddings for Mimic directly. So that means that if you wanted to play around with these exact same types of demos where you train on just the mimic embeddings without having to train an original model. That will be available to you. You know, you need to take the training and get certified, but that way you don't have to call our API and get 100,000 images back. But that API is also available to you here. You can apply, and you know, it's a fairly straightforward process for any kind of chest X-ray data set you wanted to work on. You will send your images to us, get back your embeddings, and then do what you want with them within reason. Still not unlock the clinical use cases directly, although we're working really hard to make that happen internally. You know, it's definitely something that's top of mind for us. And then also, we're hoping to extend this to other imaging modalities. You know, we figure chest X-ray was definitely the first proof of concept, but this could hopefully be very powerful in any number of other imaging domains. And you know, from there, we would love to hear again from a lot of folks like you all who have expertise in all kinds of different domains or have different ways of thinking about problems or different problems. And I guess I'll just pause there. I also have some links in here to you know, different plugs for internships, careers, all that kind of stuff. But I will pause there and see if anyone has questions.
Thank you so much. While people like wait to raise their hands, Will, are you still on? I saw you just popped a question in the chat.
Oh yeah. Okay, it says there's lots of talk about ways to give LLMs some kind of long-term memory so they can remember things from previous conversations. Are embeddings relevant in this situation? Can they be used to compress important parts of previous conversations? And do you see any uses for image classifier models with memory? Yeah, absolutely. Basically, yes to all of the above. That's definitely one of the techniques for sort of a memory or information retrieval for LLMs is embeddings. So there's a lot of really cool embeddings, like vector databases out there like Pinecone, where you can store, you may store some kind of a prompt or something, or you know, you may send your entire database to an embeddings model, and then you're able to actually query it using something like a cosine similarity to find the most relevant things to that. And then, you know, that's kind of a, you know, like you said, a compression of this. So there's also this idea of using the LLM or using a larger model as the kind of reasoner about things. So, oh, here's an embedding for this and this. What do you know about this? And send another embedding to it. And that's where I think there's a lot of really cool stuff that can emerge from that. You know, I see a potential world in which you have your kind of domain expert models where, you know, maybe we have CXR Foundation, which is the expert for chest X-rays, and someone else has an expert for, you know, completely different modality like spirometry or something. And then, you know, when you want a conclusion about that, you send it to them, get the embeddings back, get the embeddings from the chest X-ray. You combine all these with a, you know, larger model on the outside, and go from there. So another really cool thing that's emerged is that these embedding spaces for even seemingly disparate domains are not that far apart. You know, image and text and are, you know, one linear layer away from each other essentially. So there's a lot of really cool things that can happen from that. I don't know how to see who was next in the queue.
Yeah, so I see Pierre has his hand up and then Victor.
Okay.
And Will says thank you.
Andrew, thanks so much for being here, man. It's good to see you.
Yeah, thank you. Yeah.
Great talk. It's really wonderful to see some of this work and where you guys have taken it in the last year. So Shreyas and Victor, two of our PhD students, you know, they've worked with me, and done some really fun and interesting work in chest X-rays for the last few years. And I'll tell you a story about one of the challenges we faced, and I'd love to hear your opinion. So we were building a model that was trying to exceed human expert performance. So the label wasn't actually coming from a radiologist. The label was coming from a downstream image, an echocardiogram, so a higher quality image. So, you know, the idea cardiomegaly is not a very good label. Can you actually detect cardiac pathology at a higher quality level than just cardiomegaly? And so we built it at Columbia, and then we validated at Stanford with Matt and all of them there. And they basically created a new label for us on the CheckSpert database. So some of the labels did really well in translation from like train at Columbia, test at Stanford, and then some like totally fell apart. And we looked at like the pre-processing techniques and all of these other sorts of things. And, you know, the pre-processing techniques, the way the images looked, it was similar. And I even asked Shreyas, hey, make me a data set of 100 chest X-rays, half from Columbia, half from Stanford, and let me see if I can tell the difference. And I couldn't. I couldn't tell if it was a Columbia chest X-ray or a Stanford chest X-ray. But then we just trained the model on tell me if it's a Columbia or a Stanford chest X-ray, and it could do it with 99.9% accuracy. So we never got an answer as to why was the model translating somewhat poorly from one site to another. And, you know, all of the things can be true, right? So label shift, label drift, covariate shift, all of those can be possibly true. And I can't see a visual difference between the images, yet the model can tell with 100% accuracy where the image was taken. And I don't know if that matters or doesn't matter to the model. So the first question is really, when we think about the translatability of these models, and the idea of having a foundation model, because one of the other things we did is we looked at pre-training with ImageNet versus not pre-training with ImageNet, and there's really no difference. Like maybe it helped speed up convergence, but it definitely didn't lead to a performance boost. And I believe the same thing was true when we tried to pre-train with CheckSpert, but I don't hold me to that. But in general, there's a lot of things that we thought would help, but didn't. So, you know, the question I have for you is like, one, why do you think we see this persistence of performance changes from one institution to another without kind of clear localization of the cause? And two, how important do you think the pre-training really is to the overall performance of the model? Or is it more, most people are just never going to be able to have the data set size? So like if you had, you know, 10,000 images of your own at your own site, that's great. That's amazing. That's what you want, but most people aren't going to be able to get that. And do we know, you know, meaningfully how protected we are from this kind of translatability issue from one site to another, or is it always going to be an ongoing challenge?
Yeah, those are really good questions. That's really, really cool to hear about. I'd love to chat more off, you know, at a different time about all this stuff too, because it's a huge topic. But yeah, I mean, it's definitely an open question. The first question of why or how or what is it doing is, frankly, you know, this is one of the reasons why, you know, I guess I worry about the speed at which we move sometimes in this field, is because we see these things and we don't necessarily have time to dig into the why. And I would love to be able to, you know, it could be as simple as, well, I don't know if I'm sure you probably looked at like the machine that was used and all that kind of thing. But I guess to some extent, this leads into kind of the next question that you mentioned, which is sort of like, is it always a problem? And my argument would be yes. You know, I'm relatively new to ML, but even from when I started, I always kind of was curious about why. I mean, I understand, I guess on a theoretical level, why we show generalizability across institutions and different things. But the reality is if you go to deploy that, you're going to take, you know, some pilot amount of data and probably choose an operating point and do things for that particular institution for all those reasons, right? All those things that you can't possibly control for, even if you tried, right? And so, you know, my feeling would be basically more like what I think you were getting at, which is that, yes, if you have 10,000 images or 1 a million images, from your own institution, and you have the compute, maybe you do train your own model. But in the absence of that, how can we safely get past that distribution shift, so that you could actually have something that you use internally? And that's sort of where I see things being here, is that, okay, you can the few shot, or the few that you're using are helping you to bridge that distribution shift. But that's not that's also not the end answer, right? I mean, I think there's still a lot of questions of like, what is that distribution shift? And we are also we talk extensively with our the folks who internally who are experts on causal inference and all kinds of stuff like this, where how do you mitigate shortcut learning, or how do you at least take it into account? This is particularly relevant for things like protected characteristics. And the reality is, you can't really control for all of them, but what you hopefully can do is be aware of as many of them as you can. So we want to, for example, do more to publish. There are Bayesian techniques, right, that you could take, like, okay, this training distribution was on these demographics, and take some kind of a prior for that, and then adjust to your downstream test distribution. And that way you are being more careful that you're not taking these shortcuts. And again, the reality is that there's always going to be some distribution shift that you didn't think about if you were the person developing this foundation model. And you might have a completely different case for the downstream. So it's a very nuanced thing. I don't have the perfect answer for it, but it feels like that is a viable approach that you would focus on, still focus on, obviously, on learning the most generalizable representations that you can, but also admit that you're never going to learn one that is free of bias, free of shortcuts, free of these things. So essentially pass that downstream to some extent, and then let downstream folks decide what should be relevant to the downstream model and what should not be. Yeah, I don't know if that's an answer to your question, but I'd love to talk more about it, because I think it's top of mind. It always is, and it's a really tough problem to solve.
Victor,
Great answer. Thanks, Andrew.
Victor, I see a hand, and then Tony, I see that you have a question in the chat too. So Victor, if you want to go first.
Yeah. Hi, Andrew. Great talk. So I have a relatively simple question, I think. So basically, like, if I understand your approach correctly, like, your embeddings are particularly useful for setting up a binary classification problem. And so the question I have is are they still useful if you have a set of conditions that you're trying to predict simultaneously in a multi-class or in a multi-label setting, or if in that case you would just default to training a series of binary classifiers on top of your embeddings?
Yeah, it's a really good question. We haven't tried specifically the multi-class setup. My belief is that it would probably do fine on that. Obviously there's a number of other kinds of tasks that these embeddings probably aren't well suited for, at least in their current form. Things like localization or detection. We could, this is the result of average pooling across the feature maps. So in theory, you could just return the actual feature maps as well. But yeah, my understanding is that it would probably be good for multi-class classification as well. And yeah, I kind of lament that, in a lot of ways, these problems that we formulate are all sort of separate but overlapping binary classification tasks that are sort of they're definitely not independent, right? So we don't want to be too keen on kind of, but that's also exactly why it's hard, I think, to train these original models. It's been interesting to me to try to train things like multi-class classifiers, or and really they just end up being good at the most prevalent class. right? And so this is why in some ways it helps to just basically punt on that and just say, okay, do that downstream, you know, try to get as general of a pre-training as you can that doesn't overfit to any, and even then we've overfit to certain tasks, right? I'm sure we're overfit to pulmonary conditions as opposed to others. So, you know, there's more that we could do upstream, but a lot of it is also, you know, data limited and things like that. So hopefully does that answer your question?
Yeah, I think so.
Okay.
All right,
Thanks.
awesome. Tony, do you want to say what you said in the chat?
Sure, I can just say it audibly. Thanks for the talk. Just a pretty simple question. After having used contrastive learning to generate your embeddings, did you folks apply any like unsupervised techniques to like assess in the TSNE what the rough clusters might be? And also just echoing what Pierre said, if you were to have looked at these clusters, having previously worked with a bunch of healthcare embedding data, how much do these TSNE data correspond to just like where the original image came from? Because having worked with cross-site data, you often see that the same concepts might be somewhat similar, but oftentimes the TSNEs and the actual embeddings are just showing you roughly where data came from and not anything about the underlying disease.
Yeah, it's a really good question. We didn't do a whole lot in terms of applying the unsupervised techniques after the TSNE. You know, we did a little bit of a few different dimensionality reduction techniques like PCA and I think maybe UMAP. You know, we kind of at least haven't had as much time as we would like to kind of investigate that embedding space. But you're absolutely right. I haven't looked, but I'm sure that the location of the images is encoded in the embedding space, right? And again, you know, one more thing that you would probably want to, we would hopefully basically just report distributions on that. And, you know, there's some really cool work on sort of test time label shift adaptations and basically just incorporating that prior distribution into your downstream tasks. Because again, I don't know that you can necessarily hope to kind of like remove all of those things upstream or what have you. One dream that I've had for a while, but maybe hasn't come to fruition yet, is to, again, basically disentangle the embedding space. You know, like with variational autoencoders and things, you can, in theory, say, oh, here's the part of the embedding space that corresponds to, you know, the site, right? And now we can ablate that maybe if we want, or you could ablate it downstream. We might get closer to things like that with some of these like generative losses, which we've just started to look at. So combining generative loss with the contrastive, with even with the class, you know, cross entropy or something like that, that has potential for that. And that would also, again, go toward like interpretability or readability of the embedding space. That would be the dream, but you know, haven't had as much time as I would like to kind of dig into that. Yeah, thanks for the question. It's really good. Yeah.
Awesome. All right, so I think we're just about at time. So if folks don't have any other questions, can we have a final round of applause for our speaker? Thank you so much, Andrew, for joining us today. We really appreciate you spending your morning with us.
Thank you. No, it's a pleasure. And yeah, I don't know what the best way to, people can definitely find me on LinkedIn. I will also send out this presentation, but yeah, feel free to get in touch with me, talk about whatever. Yeah, you can email me as well. Yeah.
That would be awesome.
Yeah.
Thank you so much. Really appreciate it. Thanks all.
Thank you.